Furthermore, we should have, and can have, and will have, a repository where you can publish your replication work. You can publish your with the lessons you've learned from your failed experiments. Let's have that be part of the scientific literature, just as our successes are. And there's lots of hype about AI, but this one's, I think, is possible. The AI is really good at summarizing things. And so you can summarize the relevant scientific literature, and then people can criticize it, and you can make corrections of it. But people can select, you search a paper, you click the replication button, and then all the related scientific papers that are published that are related to that paper will pop up with a little AI summary. So you can just, and then you can with the buttons to click on each paper, so you can check for yourself. Instead of having, is it published in Nature, is it published in Science, is it published in Cell as the key arbiter of whether the result is true, it'll be replication. It's actually a huge inversion of how we think about truth in science, right? It'll be, and three, and this is the third thing to change the culture. We need to measure more than just what our age indices are as a measure of productivity in science, right? If you think about productivity measures in science, they're so narrow as to be laughable, right? So what they measure is volume, and they measure influence, right? Measure volume, how many papers you publish, and influence, how many citations you've had. I'm not saying those are unimportant, but those are too narrow a basis for deciding the productivity of scientists. We're going to start measuring other things. I want the pro-social behavior of scientists with regard to replication to be rewarded by statistics, right? So what fraction of your papers do you share your data publicly? Do you write your methods in ways that are easily interpretable by others and replicable by others? A lot of the behaviors that we have, do you put your tissue in biobanks so that other researchers can access them, right? So these kinds of behaviors ought to be rewarded by statistics, right? So you're not just going to go clicking over and over again on your Google Scholar page to see if your H index is increased yesterday, right? So that's, by the way, you know how to increase your H index? Here's how you do it. You if your H index is N, you find your papers that have N and N-1 citations, and get your friends to cite those two papers, and then that'll increase your H index by whatever. Don't pretend you're going to say that. So just, that doesn't. Okay. You won't care what your H index is, because you'll be judged on what you really care about, not just influence and citations. Okay, third, make big advances. The NIH must invest. Now you're reading this and think, well, this is what the NIH does. Invest in innovation, embrace new technologies, new ideas, and new approaches to old problems. This was just to justify this. The idea that the NIH automatically just does this, which I believe it does, and should do even better, is actually controversial. The existence of ARPA-H is because people thought the NIH is not doing this well enough. The key problem is that in biomedicine, we punish failure too much. What we do is we say, okay, you're a grad student. You do your experiment. It doesn't work out after a couple of years, or 3 years, or 4 years, and then you're gone. You got to leave, right? There's one of my favorite stories I learned is about a researcher named Max Perutz, who was won a Nobel Prize in 1962 for elucidating the structure of hemoglobin, right? But he was a graduate student in the University of Cambridge, and he wanted to figure out the structure of myoglobin, much simpler protein. And all his professors were telling him, this is 1951, we don't have the tools to do this, go do something else with your life. Are you crazy? Don't waste your time. You got to move on with your life, Max. Who heard that in their career? Who's heard that, right? And he just stuck with it. For a decade, he stuck with it, figured out the structure of myoglobin finally, then figured out the structure of hemoglobin, and then won a Nobel Prize. Right? We tell ourselves these stories as heroes because they took intellectual risks. And the question that haunts me is, do we have a infrastructure now, a scientific community now, that would tolerate a Max Perutz, that would encourage, that would feed a Max Perutz? I'm going to show you some data that suggests that that's not true, that we do not have such a social society, and I want to fix that problem. Okay, so first, scientific stagnation. There has been, this is from a paper by Nick Bloom, who's a Stanford economist, et al. And the question is, are ideas getting harder to find? And these are log scales. On the left is a research an index of research productivity, aggregate evidence of research productivity. And this is, so the question is, the ratio of the idea output measured by total factor productivity growth divided by the amount of research effort. And the finding, very robust, is that over time, from the 1930s on, per dollar we spend on research, the marginal benefit to economic growth, it has been declining. One theory for that is that ideas are getting harder to find. The green line is the number of researchers that we've supported. And there's been an exponential increase since the 1930s. Huge increase. If I'd given this talk in 1930, the audience would consist of 5 people, right? So it's just a very, very sharp increase in the number of researchers. And one theory is that ideas are just much harder to find now. All the low-hanging fruit has been grabbed. I'd say, like, if you look back in scientific history, you will see evidence that people say this just when huge advances happen, right? So, like on the eve of general relativity and the advances in quantum physics in early 1900s, turn of the 20th century. You had top scientists saying, well, all of classical physics has been solved, all of physics has been solved, there's nothing more to discover. And then there was a huge revolution in physics that happened just after that. We should not, even if it is true that all the low-hanging fruit is in grab, we as a scientific community should never act like that. We should always be questioning whether, does bacteria cause the ulcer, right? We should be asking ourselves, are the things we know, are there broader scientific theories and ideas that can fundamentally change how we think about everything, right? We can't act as if all the ideas are all the low-hanging fruit is grabbed. Eroom's law, you know about Moore's law, right? Every year or so, it was every decade or so, the number of transistors on a chip doubles. By the way, Moore's law just flattened out after the last decade and some, right? But Eroom's law is the overall trend in R&D efficiency, and Eroom's Moore's law backwards, and same kind of result, a reduction in per dollar spent on R&D, the returns, and this is just number of drugs that are introduced and approved by the FDA. We see the sort of secular decline over time, despite vast increases in investment. This one is interesting. This is the years of life saved per scientific paper in breast cancer. Right, so the papers in the 1970s, they had enormous effect sizes. The papers today have much smaller effect size. Now, part of this is that we have gotten much better, much better at treating breast cancer, right? So if you have a disease, breast cancer is not cured, but if you have as the disease gets sort of closer and closer to like establishing full health, the marginal benefit of additional paper is going to be lower automatically. So maybe this isn't entirely a fair comparison. In 2020, I published a paper with Mikko Pakalin. We asked, how old are the ideas that are supported by the NIH? And it turns out that in fact, okay, so let me just show you the result and then we'll describe it. Okay, so here's what we did. We looked at all of the papers that were published in biomedicine from 1940 on. Take all of the papers and all of the words and word phrases that were published in 1940 and do the same thing in 1941 and subtract off the 1940 words. And what you're left with are the new ideas that were introduced in 1941. You do that every single year, and what it looks like is a history of biomedicine that just pops out of all of the words that were published. PCR shows up in 1983, small interfering RNA shows up in 2001, so on. Look at all the papers, and then go back to the papers and ask how old were the newest ideas in each paper, right? So a paper that's in 2001 where it says the word small interfering RNA, that's a paper that's relying on a very new idea. A paper whose newest idea is small interfering RNA today is relying on very old ideas, or examining very old ideas, right? So look at all the papers that were published between 1990 and 1999, and ask what share of those papers with 0-year-old ideas, that the x-axis is the age of the newest idea input, had NIH input, NIH support. And it turned out more than half, 55% of those papers that were published with 0-year-old ideas in it in that 1990 and 1999 cohort had NIH support. Let me show you what happens if you go back 10 years into the future. 2000, papers that were published between 2000 and 2009, there was a collapse in the support for the newest ideas. If you wanted to get NIH support in the 2000-2009 era, you needed to be working on 7 or 8-year-old ideas. That's how you maximize your chance of NIH success. We became much too conservative over time. And by the way, the teens don't look any better. In fact, they look worse. How do you solve this problem? There's lots and lots, and hopefully we'll get to discuss this in the conversation, but one of the major problems is we have been doing a terrible job in supporting the career, in early career researchers, and this has been going on for a very long time. This is a very depressing graph. So this is the average age of time to the first large R01, a large grant, right? In the 1980s, the typical age of someone with a PhD getting their first large R01 grant was 36. Now, it's 42. 42. If you have an MD, PhD, God help you, because it's going to take you. You're going to be into your mid-40s before you have any chance of getting a large R01. We now require, not just your PhD, but postdoc 1, postdoc 2, postdoc 3 before you even have a chance at a assistant professor grant, and then you got to spend 2 years fighting to get a K, right? And often it's very difficult then to transition to independent science. We invest a ton at the NIH in F awards, T awards. Let me just show you just some data from the F awards. This is years. The x-axis is years since the F32 was awarded for an institution, and then the survival probability. Survival probability means what's the probability that an NIH-funded trainee stays in science, or stays in academic science, anyways. In the 1970s, just look at the left side of the graph, 0 to 3 or 4 years. In the 1970s, about 20% of people would leave science after getting an F32 award. In the 1980s, it was 75%. In the 1990s, it was 40% would leave. In the 2000s, it was half of all scientists funded with F32 would leave science within 2 or 3 or 4 years. And now in the 2010s and 2020s, we're talking about 60% of scientists leave within 3 or 4 years of getting an F award. Right? We are not doing a very good job supporting the careers of early career scientists, and it's getting worse and worse and worse. And this despite tremendous efforts by the NIH to fix this problem. The problem is one of culture, right? Max Perutz could sit there and work on his crazy idea about he's going to figure out the structure of myoglobin. It's much harder to do today. Like we ask essentially early career scientists to devote their lives to the ideas of their seniors. We need to fix that, and I have some ideas for fixing this. It's important because, okay, this is the most depressing graph I'm going to show you all today, I promise you, and then we'll just talk about fun stuff after that. This paper I published in 2016, again with Miko Pakulin. The question is, who's most likely to try out new ideas in their work, in their published work? How old is a scientist? So I have, for this graph, I'm going to introduce the idea of a career age. Career age is the year since you published your first paper. Okay, so I published my first paper in 1996. I am, very soon I'm going to be 30 years old, you guys, which is probably the only measure by which I'm 30. That's old in science years, by the way. 30 years old, right? When in your career are you most likely to try out newer ideas? As you age as a scientist, how old are the ideas in your how do the ideas in your published papers, age? Here's the depressing finding. The first 2 years after you leave your PhD is the first, and publish your first paper is when you're most likely to try newer ideas. As you age as a scientist, it declines monotonically. Roughly speaking, for every year of chronological age, the age of the ideas in your most published research science results, it also ages by about a year, right? So I'm not just relying on 30-year-old ideas in my papers, but that would roughly be the result. Nobel Prize winners, they put up a tremendous fight, right? So every 2 years of chronological age for them, their papers age, their ideas in their papers age by about a year, right? So There is still room for people with gray hair like me. On the x-axis here is the career age of the first author. On the y-axis is the career age of the senior author. That combination of early career first authors and mid to late career last authors is the most likely to try newer ideas out. So the role of mentorship is tremendously important in this. So having teams that have early career researchers trying their ideas out, mentored by senior researchers, is tremendously important. An ecosystem that encourages that is tremendously important solving the stagnation problem. Max Planck I love these pictures of him. Just look at the guy. One of the most brilliant physicists of all time, and I'm not sure I want to spend an afternoon with the guy, frankly. But one of his famous quotes, among others, is "Science advances one obituary at a time." I want to prove him wrong. I want to change the culture of biomedical sciences so that our ideas in biomedicine don't require obituaries for advance. Lots of reforms to de-risk and expand transformative research, bring some of the science of science I've been showing you into the NIH, cultivate early career talent. I'll just give you a couple. Anyone serve on a scientific review committee for the NIH? God bless each and every one of you. Thank you. Especially with the shutdown, the whole scientific community has really stepped up. We're actually not even behind, because of your all support of research. These are fundamental to getting science to advance, science to work at the NIH. These scientific review committees. But I criticize myself now. The scientific review committees tend to be very conservative. Like anyone who's ever served on one understands, the focus is on methods. The fight is almost always on, will this project work? Can it possibly work? If you have a new idea where the methods are a little bit iffy, you're done. But if you look at the narratives people produce, they're really rich. They have, this is a really cool idea. If only one worked, then it's going to be great. But I don't know if anyone's going to work, right? You've seen that. I've introduced an idea. Okay, I'll talk about consolidation in a second. This unified grant policy that essentially says the institute directors are not going to just look at a single score. Did you get a 1, 1.2, 1.3? Are you first percentile? Instead, they're going to look at the full narrative of the scientific review. And I've asked, we're no longer going to have a pay line. Instead, the portfolio has to correspond to the strategic objectives of the institute. Right? We write the amazing strategic plans about scientific opportunities in the field, and yet what ends up happening is 10 projects that look almost exactly alike that get funded because they're getting essentially a good method score, and then a whole bunch of scientific opportunities that aren't examined. So instead of pay lines, we're going to say, look, if you have a portfolio, the institute directors, I'm going to tell them, look, if you have a portfolio and you take scientific risks, you say, okay, I'm going to fund 50 projects and I don't know if all of them will work. But if 49 of them fail and 50th cures type 2 diabetes, that's good. That's a really good portfolio, right? This will help early career researchers, because it's early career researchers that are proposing newer ideas that don't quite have the method support of the community. This will help the problem of stagnation, because we will be able to take scientific risks, and I don't want to punish the failures. I want a place where you can publish those failures and describe what lessons you've learned from them. This happens in Silicon Valley, right? So if a VC funds 50 projects, 49 of them fail, and the 50th is Google or something, that's a great portfolio. I want to bring that spirit, rather than just pay lines that are going to drive it. It's going to be, what are the scientific opportunities that are going to drive the decisions? We've consolidated the first level grant reviews so that the big thing is expertise and resources. I was a professor at Stanford University. I've talked to people now who've moved from top universities to less well-known universities, where they submitted the same grant twice. And they always get a worse score when they move to a less well-known university. I also took her the other direction. We punish people at universities that are not traditionally seen as centers, even when they have great ideas. So now what we're going to do is, instead of asking a numerical score of how good a scientist are you, where inevitably the Nobel Prize winners get ones or whatever, and then the early career scientists are disadvantaged, the question is, do you have the expertise and the resources to do the research project that you proposed? A 1-0 number. So that the emphasis is on the idea. Of course, the researcher matters, but researcher only matters in this evaluation to the extent of in the judgment of this review committee. Do they have the expertise to do the work? Okay, I'm gonna stop because this is like this. I've gone on way too long, but I gotta say this. We're gonna double down on training grants. I've heard a lot of criticisms last year, but probably the one that hurt the most is somehow I'm against support for early career researchers. I want to tell you, I think if we don't solve this early career researcher problem, we're never going to get out of this stagnation problem. We have to change the culture of science and scientific funding so that early career researchers have a chance at trying their new ideas out. I want a nation of Max Peruz's. I mean, I want you all to try, you early career researchers in the audience, I want you to try out and encourage people to sign on. I'm not promising you success. I can't promise that. Max might have failed, but I'm promising you a shot at trying your new ideas out. And we're going to think of new ways of like doubling down on these. More training grants, less onerous paperwork for early career scientists who don't know how to navigate the crazy Byzantine paperwork of the NIH. We're going to figure out how to like make this better. If I don't solve this problem, then I'll view myself as a failure as NIH director. Okay, and I'm open to your ideas. We need a culture shift. I'm gonna end here because I want time for the conversation, but I want to thank you for coming out. I want to thank you for those of you who've done reviews for the NIH, who've gotten NIH grants. The NIH, you all are our partners, and I'm so grateful for the support from the scientific community, for the continued support from the scientific community for the NIH. Our mission is really noble. We will make America and the whole world healthy through science. Thank you so much.